Hello, everyone. Can somebody use the Q&A to let me know that you guys are hearing me? So you cannot hear me? Okay, great. Okay, so let's okay, thank you. Okay, so let's before I get started, I have to make an announcement. Majority of the class has submitted their peer review. Some students haven't, and the deadline has passed. So this time we're going to extend the deadline for a couple of hours this afternoon to let those people submit their peer review. If they don't, then we consider them as voting or rating themselves and others as 0. From next deliverable, the deadline for submitting the peer review is 1 hour after the submission of your deliverable. Okay, so that's the only the only announcement I had. Okay. I have a lot of slides to cover today, so let's get started. We were discussing implementation of Mutex, different implementations. So the latest implementation that we discussed was using interrupts and a lock variable. So I don't actually want to go through this. Okay, so let's do some discussions. Why do we need to disable interrupts at all? At this point, we're enabling and disabling interrupts when we want to access the internal state of the mutex, which is a shared object. All the threads that use this mutex can change those variables. So every time a thread acquires or locks a mutex, it changes that mutex's internal state. And because every thread that uses that mutex can potentially lock or unlock the mutex, therefore the state of the mutex, the queue and the variable that we defined are considered shared objects. So we're using interrupts and disabling and enabling interrupts to manipulate the internal state, and that's why we're using it. The good thing here that makes this implementation different from the previous implementation is that the duration of time that we're disabling interrupts is very, very short. Of the threads that are using this mutex, the interrupts are disabled during the entire critical section, which could be potentially long. Here we have only disabled interrupts when we're changing the internal state of the mutex. So the critical section, that the interrupts are being used for is basically just checking if the value is busy or not. So actually, let me get rid of my own video. Okay, so yeah. So therefore, this is an improvement on the previous implementation. Okay, so let's talk about enabling interrupts again. If you look at this code, this is when you lock the interrupts. You're going to disable interrupt at the beginning of it. And then at some point, you're going to call thread switch and go to sleep, which basically means that you disable interrupts and then you go to sleep here after calling thread switch. What happens to interrupts? When should we enable interrupts? So the first option that we have is to enable interrupts here, right after we check to see if the lock is busy or not. The problem with this one is that this is too early to enable interrupts, because if you enable interrupts before you put yourself to sleep, somebody else can wake up, the one who had the lock maybe, and then see that there is nobody in the waiting list. So if you look at the unlock code, the one who wants to unlock, if that thread wakes up after you enable interrupts, maybe timer goes off and then there is a context switch and the thread that wants to unlock wakes up. That thread checks now the waiting queue, and nobody is there because you haven't still put yourself there. So they would just return they would make the value empty and return without waking you up. So basically, you will get stuck in the waiting queue forever. Nobody would come and wake you up. What about here? Right before we call thread switch, is this a right place to do this? Again, no. The reason is, let's say you have put yourself in the waiting queue, and you still haven't context switched to another thread. But let's say an interrupt happens, and then some other thread, the one that has the lock, wakes up, and then it wants to unlock. Now that thread sees that you are in the waiting list because you have already put yourself in the waiting list. So that thread will wake you up, meaning that it will get you out of waiting list and make your status ready, and then terminates. Now, let's say you come back again. When you come back, where do you come back? You come back here. You think that you're still gonna go to sleep. So you again call this thread switch and you context switch, and again you get lost. So you were to have the lock and continue, but now you actually put yourself to sleep. So I got a question. I would assume that it's a private question, but the answer to that is that yes, we're going to open the Dropbox for a few hours. I'll send an email about the details of it. Okay, so where should we actually enable the interrupts? After thread switch, we should enable interrupts, or right before? How does it gonna work? Well, this is where we are going to have this invariant that we will have to make sure that we will stick to throughout our implementation. And that invariant is that it is the responsibility of the next thread to run to re-enable interrupts. Let's look at this example. Let's say we have two threads. Thread 1 disables interrupts and then calls thread switch. At this point, you have a context switch. Thread B wakes up from its own thread switch. The first thing that this thread should do right after it comes out of thread switch should be enabling interrupts. And then this thread does some work, and at some point it also disables interrupts, calls thread switch. We context switch, we come back. Where do we come back? We come back inside this thread switch in thread A. We return from it, and then the first thing we're going to do is to enable interrupts, which if you go back and look at the code in previous slide, you exactly see this. So the moment you come out of thread switch, you make yourself state running, because now you're running again. And then when you get out of that if else, the first thing you do is you enable interrupts. And this is an invariant that should be carefully implemented in all threads. Whenever somebody wakes up, they have to enable interrupts. Okay, what are the problems with this implementation? The first one is that still we cannot let the user libraries to implement their own locks with this method, because this method requires disabling interrupts, and disabling interrupts is a privileged mode instruction that could only be executed by kernel threads and kernel code. So user space libraries cannot really implement mutexes like this. The other problem with it is that it won't work well on multiprocessors. And the reason for that is basically disabling interrupts would just disable interrupts on one processor, and it would require message passing between different threads. I just remembered one more announcement that I forgot. Yeah, so let me come back on the screen and make that announcement. So, okay, the second quiz is going to be up after the class. I just forgot to mention that. Again, the deadline will be by Friday, 11 a.m. in the morning. We are still trying to regrade previous quizzes. We have found a way to do it. We'll try. Worst case scenario, we'll do it manually. We're just trying to use the system, but so we'll regrade quizzes with a new grading rule. One more thing about the quizzes I have to mention, because this point that I'm going to make now is asked in a question or two of the quiz, which kind of relates to ECE 252. Sorry, yeah, ECE 252, but I'm going to still make it. So in a process that has multiple threads, there is one thread that is considered the main thread, which is basically the first thread that was running inside that process. That is the main thread of a process. That thread probably created other threads and so on and so forth. So that main thread, if that main thread returns, all the threads inside that process will die, will terminate, no matter where they are. They're waiting, they're ready in the ready queue, no matter where they are, they all get terminated because the process has terminated. And the process terminates when that main thread terminates. So as long as that main thread hasn't terminated, everything goes as intended by all the system calls you create, you join, and such. But the moment that main thread exits, no matter where you are in the queues and your status, you'll be terminated because the process has terminated. So should all the other threads inside that process. Okay, I just wanted to make this point before the exam because it's been asked in the exam. Okay. Back. Okay. So alternative solution to this take 2, which will bring us to take 3, is to use atomic read modify write instructions. Let's look at a bunch of examples of these instructions. So here, this is again probably a recall. You've seen it in ECE 252. So this is just an explanation, a pseudocode explanation of what these instructions do. This is not exactly how these instructions are implemented. So you just execute one instruction test and set, and then hardware does this instruction atomically. And what that does is it checks that address that you pass to the test and set. It makes that whatever the value inside that address 1, and then it returns whatever was previously in that address. And it does so atomically. And by that, I mean all 3 of these would happen at the same time. So nothing will nothing would interleave these instructions. So all 3 of them will happen from the perspective of all the other instructions in the system as one atomic instruction. That would, the same way that load is atomic, so if you look at load itself, you're executing multiple instructions, sort of. You're sending the address to the memory is reading that block, and then the memory is sending back the address. But from the perspective of all the other instructions in the system, a load is atomic. So you execute load, and then you have your data. The same here. You execute test and set, whatever you had in the address comes back, and then you should expect that the value in that address to be 1 from now on. Then you have swap, you have compare and swap. You can look at them. We actually will use compare and swap later on in multiprocessors when we talk about scheduling. I will probably maybe I can say, so with the swap, you have an address in memory and you have a register. What you do is that you first read what is in the address, then you change the value in the address to be your register, and then you make the register to have the value in that address, the previous value. So basically you swap whatever is in the address and whatever you have in your register. And again, all of it happens atomically. Then you have compare and swap. What this one does, it gets an address and 2 registers. It checks to see if what you have in the address matches the register 1. And if so, then it changes that value to register 2 and it returns success. But if the value in address the value in the memory at the address that you gave does not fit or is not equal to register 1, then you get a failure. And again, all of this happens atomically. Now, we're going to use test and set to implement something that we're going to call Spinlock. And it's the idea of a Spinlock is very easy. It's very similar to interrupts. So let's look at it. So we're going to define class Spinlock that has, again, one variable, which is the value of the Spinlock, initially 0. And then it's going to have 2 functions, lock and unlock. I got a question. So compare and swap doesn't actually swap. Seems like it just sets values. It basically does, right? Because it first checks that the value that you have in the address matches register 1, and then it makes it to become register 2. So it's as if you're, or in the sense that yes, it doesn't change those 2 registers. It's about that memory. So it basically, let me publish this question. Yes, you're right. It doesn't swap those two registers. It just swaps whatever is in that address that you are expecting it to be register 1, and now you want it to become register 2. So if your expectation is correct, that in that memory you actually have the value of register 1, then you swap it with the with register 2, and otherwise you just return failure or false, whatever. Okay, that was a good question. Okay, now okay, so that's it. So this is class Spinlock. It's declaration and its implementation together, right there. So let's look at it. There is no queue here. We don't have a queue of waiting threads anymore. There's only a value and 2 functions. The unlock is very easy, just sets the value to free. The lock has only a while instruction that always executes test and set. So now if the value is 0, this test and set is going to return 0 and then set the value to 1. But then because it returns 0, this while breaks and you can go in. So this lock function will set the value to 1 and then exits. However, if the value is 1 and then you execute test and set on that value, test and set is going to set it again to 1, so nothing is going to change, but it's going to return 1. And if it returns 1, then this while loop continues. So you keep doing while here, which means that you're going to wait. Now, the reason that we don't have a queue is that threads that execute lock are busy waiting. So they're still waiting because they're executing this while, but they're actually executing something. So their state doesn't change from running to waiting or from running to ready. So they're still running. They're still wasting CPU cycles, but they're actually waiting. So they cannot get in out of they cannot get out of lock as long as the value is 1. Until someone sets the value to 0, then at that point, one of those threads that are executing this lock will see that one and then gets it unlocked. Okay, I explained these. So first of all, what is wrong with this implementation? Well, obviously, this is not efficient in terms of waiting. You're doing busy waiting, right? You're wasting CPU cycles. Now let's have some discussions. The upside of this is that we got rid of interrupts. And all the instructions that you saw in the previous slide, they can all be executed in user mode. So we can actually allow a user mode library to implement their own mutexes. The other good thing about it is that it actually works on multiprocessors. There is nothing about this that would restrict us to uniprocessor. What are the downsides? As we mentioned, busy waiting is the downside. And that busy waiting actually causes other problems. The most obvious problem that could happen is that the one thread that wants to release the lock could be delayed, the execution of which could be delayed because other threads are executing their test and set. And that could actually lead to priority inversion. So a high priority thread comes in, they want the lock, which they want the mutex. The mutex, so yeah. So if the busy waiting thread has higher priority than the thread that wants to unlock, then that other thread with lower priority would not get to execute because the higher priority would be scheduled, and that higher priority is going to just keep executing that that while loop, and there would be no time for the lower priority to execute, and that could actually even in some cases lead to deadlock. So busy waiting is, we'll see that we're going to use this Spinlock to implement Mutex. So there is no way to avoid it in some sense. But if you actually make it as a method for you, so if every time you want to implement locks, your design, you have busy waiting and it's unbounded, then you could really get bad performance because again, if you have busy waiting in your semaphore or your monitors, and people are using those to protect their critical sections, then the entire time that the other thread is inside that critical section, those that are waiting are actually busy waiting, and they're wasting CPU cycles. So you're going to avoid busy waiting at any cost. Now, there are certain scenarios that you actually cannot eliminate busy waiting, especially if you want to use test and set, then busy waiting is always there. Now, we're going to use busy waiting, but we're going to dramatically make it short. So if a thread is going to busy wait, let's make it as short as possible, the same way we did with interrupts. If we were going to disable interrupts, let's make it as short as possible. So here is an implementation of Mutex. This is take 3. We're going to use a Spinlock. So the only thing I've added here is a Spinlock. I still have my Mutex value, and I still have the waiting queue. I've added a Spinlock. We're going to call it Mutex Spinlock, and we still have those two functions. Now, this is the first time you're seeing this one. We're going to introduce a class called scheduler. And this scheduler is going to have the ready queue, and it has its own Spinlock. So this scheduler also has the Spinlock to protect this ready queue, this ready list. And it has 2 functions, a suspend, which puts a thread to sleep. The thread that calls suspend will go to sleep. And then it has another one that is, we call it make ready. It's going to make a new TCB ready to execute. Okay, so one point before we go, this Mutex Spinlock that we introduced, we're going to use it whenever we want to change this value or whenever we want to change anything inside the waiting queue. This is Spinlock. We're going to use it every time we want to change the ready list. Okay. Mistake again here. Okay, so let's look at the implementation of lock. The first thing we're going to do inside is we're going to use our Spinlock to protect inside the lock function, because we're going to change the internal state of the lock, the Mutex. Very, very similar to what we did with Mutex. With interrupts. when we disable the interrupts. The concept is almost the same. So here we just check if the value is busy or not, and if it is, then we put ourselves to the waiting queue of this mutex. So this is the waiting queue of the mutex, and then we call upon the scheduler to suspend us. We're gonna pass the mutex Spinlock to the scheduler, because if you remember with the interrupts, we had this invariant that whoever goes to sleep, the next one will enable interrupts. Here we have only a mutex, so we're going to pass the mutex to the scheduler so that the scheduler can indeed free the mutex. Because if we go to sleep while the mutex is locked, then nobody else can access the internal of this mutex. So this, we're going to give it to the scheduler, this task to scheduler to unlock this mutex after it puts us to sleep. We'll see the implementation of suspend. And then here, the else, if basically the value is busy, we just unlock the scheduler, the Spinlock, and now we have it. So if the value is free, then we make it busy. Now we have the lock. So we have the mutex. We have locked the mutex. Now let's look at unlock. Very similarly, we lock the Spinlock. We want to release the lock. So we want to unlock the mutex. We check if somebody is waiting on this mutex. If so, we will choose one of them. This remove could have any type of policy that we have in mind. We could remove the first one that called lock and got blocked, or whatever policy that you could think of. So you pick one, and then you send the scheduler, you tell the scheduler, make this TCB ready. And by the way, here you don't actually release the, sorry, yeah, that's it. You don't change the value. You don't change the value. You don't make the value free, because the next thread that will get executed will assume that they have the value to busy, because they would wake up here inside their if, and as you can see, they check the value was busy, and if they wake up here, they still assume that the value is busy, so they don't need to make it busy. All it means that now that I woke up here, it means that I have the lock. So the busy corresponds to me. And if there is nobody waiting, then make the value free and then unlock. Now I have a couple of questions that I'm going to actually give you a few seconds to think about before I give the answer. These are very important questions. The first one is, can interrupt handler use this lock or this mutex? Let's say we have a shared object between kernel threads and the interrupt handler. Can interrupt handler use this mutex to make sure that only one thread basically accesses a shared thread, a shared object? Okay, the answer is no. And the main reason is that interrupt handler is not a thread. So interrupt handler cannot be suspended. Interrupt handler cannot be scheduled. And as you can see here, if you want to acquire the lock and the lock is busy, then you're going to be suspended. Well, an interrupt handler can never be suspended. Therefore, interrupt handler cannot use this mutex. So then the question is, how should we actually protect data that is shared by the interrupt handler and a kernel thread? The answer is that the first option is to just use a Spinlock, because the Spinlocks, you can use them, right? they don't acquire scheduling per se. The problem with the Spinlocks is that priority inversion that we talked about and the potential for deadlock. So let's say a thread has acquired that Spinlock that the interrupt handler wants, and then an interrupt happens, and now interrupt handlers comes up, and then interrupt handler tries to acquire that Spinlock. Well, in this case, the interrupt handler is going to busy wait. For how long? Basically forever. Because interrupt handler in usual general purpose systems has the highest priority. When an interrupt happens, we're going to call interrupt handler. Now the Spinlock is locked by another thread, so the interrupt handler is going to just busy wait forever, and we have a deadlock. So to use a Spinlocks that are shared between the interrupt handler and threads, you have to be super careful. So in some sense, you have to avoid keeping an interrupt handler, locking a Spinlock and going to sleep. Or there has to be a way that whenever a thread, you have to implement this invariant that if a thread gets the Spinlock and gets interrupted or goes to sleep, that Spinlock should be released. Now, there are other ways also. You could also use, I think I don't have it in this slide, but in some cases, we actually want to use semaphores. We'll explain that later on. Okay, so let's discuss, wait a second. Let's discuss this take 3. First of all, why do we disable interrupts? Again, a problem with the animation. Now let's look at the scheduler. We just saw how the mutex is implemented. Let's look at the scheduler part of it. For implementation of suspend, the first thing we're going to do, we're going to disable interrupts. We're going to acquire the Spinlock's lock because we want to change the scheduler's Spinlock because we want to change the internal state of the scheduler, which is that ready queue. Now, once we have done all of this, we're going to unlock okay, let me go back, make a correction here. So yeah, here, if you want to, I actually have it in the slide, but I didn't have it in my explanation. So if you want to use a Spinlock between kernel threads and an interrupt handler, the moment you acquire the Spinlock, you have to have disabled interrupts. You have to make sure the interrupts don't happen. I think I mistakenly said that you have to have an invariant that you would release the Spinlock, but that's almost impossible. So the way to get around this is to disable interrupts. So before you acquire the Spinlock that might be used by an interrupt handler, disable interrupts so that you make sure that no interrupt handler will will run when you have the Spinlock locked. Okay, sorry about that. Now, Here we disable interrupts, we acquire the lock of the scheduler. We now at this point release or unlock the spin lock that was passed to us, which would belong to the mutex. And we proceed to suspending the thread that called us. So basically the running TCB, the state of running TCB becomes waiting. We choose a new thread and we switch to that new thread. Whenever we come back here, exact same concept. If we come back from thread switch, now we are gonna go back to the thread that executed suspend. So we're gonna make it running, and this again return unlock the scheduler, enable interrupts, and return. Now for make ready, disable interrupts, acquire the spin lock, choose. Sorry, now we want to make ready a TCB that was waiting, so we just add it to the ready list. That's all we need to do. So this TCB that we want to make ready previously was waiting. Now we want to make it ready. We just add it to the ready list. We make the status of that state of that thread to ready, and we're done. We unlock the spin lock and we enable interrupts, and that's it. Now, a few questions about this one. Why disabling interrupts? I kind of alluded to it when I went back to the previous slide. The reason that we're disabling interrupts here is because the scheduler's spin lock is a spin lock that with high probability will be used by the interrupt handler. So this is a very important spin lock. The interrupt handler may or may not want to schedule another thread or do something else. So it might actually need this scheduler's spin lock. And if we don't disable interrupts, and here we lock that spin lock, and then an interrupt happens, then we have deadlock. Because then that interrupt handler could busy wait forever while we're holding the lock. Okay, so the other question that I'm asking here is that what would happen if we unlock the mutex as a spin lock before suspend? So here we pass the spin lock to the scheduler to free. What happens if we actually unlock this before calling suspend? So you can go and convince yourself that this could actually lead to the same problems that we had with disabling interrupts. So if you disable interrupts anytime before you context switch, you will have a problem. That's why the same concept here. You don't really want to do it. I think I need to save this. My laptop's fan is working and then it's creating a sound. Don't exactly know what else. Yeah. Okay. Still. Okay. Talked about that. Okay. So just a comparison to put side by side the two implementation we've seen. One with disabling interrupts, and the other one. Okay, so one with disabling interrupts and one with the spin lock, you can see the similarities. So here, instead of disabling interrupts, we lock the spin lock. Instead of enabling interrupts, we just unlock the spin lock. The rest of it is basically the same. Just to recap, this is how we use locks, use mutexes. gosh. Okay, so this is how we use the mutex. We lock, we access critical section, and then we unlock. So the first implementation we saw was basically disabling interrupts and enabling interrupts. The problem with it was that, well, it's the entire critical section, the interrupts are going to be disabled, so no activity other than this thread could happen. And when you exclude the activities, you're basically also excluding OS activities, which is dangerous. Then we improved this implementation. We introduced the extra variable that we used, and by doing that, we basically disable interrupts only when we're checking the state of the mutex, not for the entire critical section, which was an improvement. But still, the problem with this was, again, that disabling and enabling interrupts are instructions that only OS can use, and we don't really can give this implementation to user space library. So then we came up with this Spinlock implementation, the same process. We first implemented it with just vanilla test and set. The problem with this implementation basically was busy waiting. So while one thread was inside its critical section, the other threads were busy waiting here, which is not something that we want. So we improved this implementation by doing the same exact design. We implemented it by using a variable. We called it value, the value of the lock, and we actually put the waiting queue here, and we used the scheduler to put a thread to sleep and wake threads up. Now, if we want to see how mutexes are implemented in Linux, well, you probably would assume or expect to see more optimized design. One optimization that is usually done is the fact that most of mutexes are free most of the time. Again, this is not all the time, but most of the time mutexes are free, so we can take care of we can take advantage of this. The other thing that we can take advantage of is other atomic operations that hardware provides. Other than test and set, there are other very powerful atomic operations that we can use. So the way that this works is that in Linux you have a fast path and a slow path. You're going to use all those two facts above to implement your mutex. So in the fast path, you only check the mutex, and if it is unlocked, then and nobody is waiting, then in 2 instructions you lock it and you go. So you are now in your you have acquired the lock, you have locked the mutex, and you can go ahead and enter your critical section. And this only happens if nobody was waiting. But if anybody is waiting, then you just call the slow path. So you just call into kernel, and you use the other implementations that we've seen. So let's see how that works. So in Linux, instead of a class, we have a struct. We have a counter. We're going to tell the compiler that this is an atomic counter. It means that any increment or decrement on this should happen atomically. We still have that mutex, and we still have the queue. So the only thing that has changed is that instead of the value that we previously had in our mutex, now we have a counter. Now this counter is going to act as that value, but it could have any value other than 0 and 1. So we're going to have an invariant that says, okay, if this is 1, this count is 1, then it's unlocked. And if it is anything less than 1, then it's locked. Now, in order for you to lock it, this is the fast path. So in few instructions, you're actually gonna here this lock that you can see here. The lock decrement means that I want this decrementation to happen atomically. So you basically decrement the value of count. And if the result is not 0, it means that it was less than 1. But if it was 0, so if it was 0, you don't jump, you just go. Sorry, jump, not 0. If value is now 0. Okay, if the value is now 0, it means that you have locked it, so you jump and you do your critical section. And if the value is anything other than that, it means that it was already locked, so you have to go through the slow path. So yeah, I explained. This lock decrement means that do the decrementation atomically, because you have that atomic count. And it actually assumes that you have that count in EAX in this code. So you first load it and then do the rest. Or you put the address of it in EAX, the address of counts, and then you decrement. Okay, so a discussion, probably last discussion on Mutex. We've seen a couple of implementations, probably 1, 2, 3, 4, 5 implementations already of Mutex. So when you want to lock a mutex, the way we have implemented so far, we have called a function. So the lock was a function. So you do a function call to lock a mutex. This works well for kernel code, and everything that we've talked about was assuming that the threads that are going to use these locks are kernel threads. If the threads that want to use the lock are user space threads, then by definition, they're going to use system calls. Now, system call is a little bit different than a normal normal procedure call. And the way that they're different, they're going to do all sorts of other things. They're going to disable interrupts. They're going to save the state of the TCB somewhere. So they're going to do stuff that we didn't, account for. We assume that this is going to be just a This is going to be just a procedure call. But that being said, the ideas are there. So the ideas that we provided would work. You only need to do some other stuff to make sure that when you call a system call, then your stacks are aligned. Whatever you have in the stacks are the right things. So there will be some more details to take care of, but the general ideas are there. The other thing that I can say is that you can actually, now that you have test and set, you can actually be independent of kernel. Instead of calling system calls to acquire a lock, you can, if you are a thread library, the same way that you can have your own scheduler, your like green threads, the same way that you can do those, you can actually implement your own mutexes. And if you are wondering, now we have blockings that would happen when you call lock on a mutex that has already been locked. You also have timer interrupts that happen. How do these two could interleave? I'm not going to go through it, but good news, it's going to work out fine. So as long as you stick to all those invariants that we talked about disabling interrupts, enabling them back, about whose job is to do these, as long as you stick to those and you implement them in all your design, then the system should work smoothly. Okay. I'm going to give you 2 minutes to get up, stretch, yeah, take a break, and then in 2 minutes I'll continue. Okay, we're back. So if you, again, as a recall, rules to take care of when you're using mutexes, always initiate a mutex to be free. Never access your shared data without locking the mutex that is corresponded to that shared object. The best place to lock a mutex is the beginning of your function. That gives you much better readability to your code. And the best place to unlock it is at the end of your function. And never throw your mutex for someone else to unlock. So this is one example. I'm going to go through it very fast. That shows the importance of accessing shared data while holding the mutex or locking the mutex. So here is a function that is going to return p. So what it does is that it first checks to see if p is null, and if it is null, then it acquires or it locks a mutex. It creates p. It unlocks the mutex and it returns p. So this is kind of like an optimization that you might think. So you might say, instead of every time I want to get p, instead of acquiring the mutex and then checking if p is null, then create and then release them or unlock the mutex and return, this is going to take a lot of time because I'm going to just create p once. Let's say this is a single tone design. So p is going to be created only once. But then because of that only one time that p's state is going to change, if I do the mutex at the beginning and at the end of this get p, then I'm actually requiring all the future threads to compete for this lock. And if I have a lot of threads that want to read this lock, it's going to be contention, and only one of them at each time can actually execute this. So for performance reasons, you might actually think that this is a good implementation. Now, does this work? I usually pause again in physical classes and let students think about this. I got a question that says, what happens if we switch to a new thread whose next instructions wouldn't be the one after returning from a previous thread switch call? So this could actually happen only in one thread. So, and that would be a thread that was newly created. Every other thread that you would switch to has to have previously called thread switch. You can think of all the ways that you can context switch a thread, and that would boil down to voluntary or involuntary events. In both of them, either a system call handler or an interrupt handler will be called, and then they would call switch. So you're always going to call switch, context switch, when you want to context switch. So whenever you come back, you're going to come back from there. The only place that this is not going to be true is when you create a new thread. So that new thread never has called thread switch. But then as we described and we explained, we take care of that by just pushing a dummy stack frames and imitating that. And in our own project, we actually take care of it inside the thread switch. So we check if the task is newly created, then we switch differently than if the task has already been context switched on. Okay. Now going back to this question, so this doesn't actually work well in real hardware, and the reason for that is that the compiler or the hardware could potentially reorder these instructions. And what happens if the reordering happens? So if you reorder, by that I mean you execute, let's say, this instruction before this instruction, because if you look at these instructions, this instruction sets temp to an area in memory. These two instructions afterwards, they depend on the first instruction. But then this third one is independent of these two. It only depends on the first one. It only depends on temp. So once after this is executed, you could potentially reorder between these three because they're independent of each other. Now, let's say you do so, and while you're doing this, so you execute this first one, you set P to temp, but you haven't executed any of these two. Let's say you context switch, someone else comes in. Now someone else checks if P is null, and well, P is not null because you have already executed P equals temp. At that point, they think that P is initiated, so they return P. Well, P is not initiated because you haven't yet set the fields of P. So in this case, you're going to have a problem. And this is called actually double-checked locking. The simplest way to get rid of it is basically use locks at the beginning and at the end. This is the safe way to do this, although it will introduce a lot of performance overhead, as I mentioned. So yeah, somebody's asking, so a new thread should be re-enabling interrupts right away to maintain the invariant. That's a very good point. Yes, it should. And if you go back to my slides, when we called about stub, and there was something housekeeping before we call the function, and if you look at that slide under what is done in housekeeping, you can get stats and stuff. One other thing that you can do is to implement this invariant, so you can enable interrupts in that stub. This is one of the things that you can do. Yes, that was a good point, good catch. Okay. Now, let's talk about smart semaphores. You dealt with them extensively in ECE 252, so I'm assuming that you know a lot about them. A it has two functions. I have a very nice animation that I spent hours and hours to make, but because you know about me smart semaphores, I'm going to just skip it. Such a waste. But anyways, okay, let's implement semaphores. But just as a recall, so semaphores have two functions, right? P and V. We're going to, so P, both of them are atomic. P waits for the semaphore, the value of the semaphore to become positive, and then it decrements it. And V basically just increments the semaphore's value. And it wakes up whoever previously has called P. So it wakes up one of them. Okay, now let's implement it. Very close to how we did with Mutex. We're going to have a Spinlock for our semaphore, and we're going to have a value for our semaphore. At the beginning of P, we lock our semaphore's Spinlock. If value is 0, then we have to wait. We add ourselves to the waiting queue, and we call suspend, passing to it the semaphore's mutex, the semaphore's Spinlock. And a mistake here, it should be semaphore Spinlock. And else we just decrement the value. Here is a semaphore V. So this, what does it do? Semaphore V will check the waiting queue. If anybody is waiting, then it picks one and it schedules them or makes them ready. Otherwise, it just increments the value, releases the lock. Now, the question is, can interrupt handler use this semaphore? Very similar to the answer we gave for Mutex, a little bit different. So the semaphore definitely cannot use P because it cannot be suspended. But it could potentially use V. So the semaphore could potentially use V to increment the value and wake somebody else up, which basically is how it's used in Linux kernel. Semaphores are extensively used in Linux kernel, and this is one of the use cases where either the device driver or the interrupt handler use this the semaphore, but they don't wait for it. They just use it to signal other threads. This is basically kind of like signaling everybody else who is waiting for this semaphore. So as long as you don't suspend an interrupt handler which cannot be suspended, you should be fine. So if that's something that you want to do, if your semaphore is going to be used by interrupt handlers, then you should remember to disable interrupts here and enable interrupts here, both of them for P and V, because then if your interrupt handler is going to use V, then by definition they're going to use this semaphore Spinlock to lock it. So you better protect this these two sections by disabling and enabling interrupts. Again, so if that's the design that you want to go with your kernel, if you want to have semaphores that are being used by interrupt handlers, then you have to protect them by disabling and enabling interrupts. Because then that Spinlock, the semaphore's Spinlock becomes the point that could cause deadlock, as we discussed. I don't know how much this was emphasized in ECE 252, but generally speaking, for multi-programming and multi-threading, semaphores are not recommended. And this is what we usually tell students. Don't use semaphores. Know how they work, because if you get to read kernel code, you need to understand them, but don't use them yourself in your code. This is from Dijkstra's own paper, and this is Dijkstra's own handwriting. I mean, this is a font I'm using with Dijkstra's handwriting. But this is what he says. So he says that we actually introduced semaphores, but then we started using them for two completely different tasks. We started using semaphores to implement mutual exclusion. That's when you initiate your semaphore to 1. Basically, you introduce a binary semaphore, which you've seen pretty much in ECE 252. That way, basically, your semaphore becomes a mutex. You're also using semaphores for scheduling and signaling. Basically, that V function that we talked about, P and V, it's kind of like a signaling that is happening there. So basically, a scheduling, who's going to get to go now, who's going to wait, that is also happening by semaphores. So this is not a clean design. It doesn't have modularity. We're implementing two different functionality in one module, which is not perfect. So instead, what should we do then if we're not going to use semaphores? You've seen monitors and condition variables. Well, exactly. So you basically divide these two to different modules. If you want mutex and you want mutual exclusion, use mutexes. If you want scheduling and ordering and signaling between threads, then use condition variables. So the problem I just described, the solution is monitors. So monitor basically includes 1 mutex and 0 or more condition variables. Now, what are the functions if these are all recalls? What are the functions that we define on a condition variable? So so as I said, monitor has 1 mutex and 1 or more condition variables. So all the condition variables inside a monitor, they all work with the mutex inside that monitor. So when you wait, you pass the mutex. This wait will atomically unlock the mutex and relinquishes the processor. Basically puts the thread to sleep. And then you have signal that would wake up a waiter. And then you have broadcast, which will wake up everyone. Properties of condition variables. The first property, again, these are recalls, hopefully will help to bring memories back. So the first and most important property of condition variables is that they're memoryless. They don't have any memory in terms of previous calls to signal. So if there is nobody waiting and somebody signals or broadcasts, the signal and the broadcast on empty queue will be lost. So nobody will, if after a signal somebody waits, they're not going to get the signal. Now compare this with a semaphore. In semaphore, if somebody previously has called V, that V got memorized because the value has got incremented. So next P will benefit from it. It's not memoryless, it has memory. But here, signal and broadcast will be lost if nobody is waiting. Always, always, always lock the mutex before calling any functions on your condition variables. If you're going to call wait, if you're going to call signal, if you're going to call broadcast, the implementation that you're going to see in the slides will assume that you already have acquired the lock, the mutex. they would assume that the mutex is already locked, and then these functions are being called. Again, because we're using monitors, and monitors for each condition variable, we definitely have to have at least one. There should be one mutex. So that's the structure of a monitor. You have one mutex and bunch of condition variables. So you might actually see some people saying that you really, for signal or broadcast, you don't need to have the lock, but please just ignore those optimizations. They're just optimizations that could cause problems. Calls to wait signal and broadcast, all of them are atomic. The other thing to pay attention to is that when a thread calls signal, in most implementations, we'll talk about this. In most implementations, all the signal does is that it makes a waiting thread ready. It doesn't jump to it. It's very much, it's not like you pick some waiting thread and then let that guy execute. You just make the waiting thread ready, and then you continue executing. So you don't relinquish the processor time for the newly created thread. Sorry, newly awakened thread. So I guess I'm gonna, can I do this in 1 minute? Let's try to go through this slide in 1 minute. So this is one example using monitors to implement bounded buffers. So we're gonna have two mutex for this. So let's say, what is a bounded buffer? It's kind of like a FIFO, but it has a limit on its capacity. Let's say the maximum capacity of this buffer, we want it to be max. And then we have two functions, produce and consume. So the producer will put items on this queue, and then consumer will consume. We want to do this with mutex, basically with a monitor. So the way we define it, we define one monitor, which has one mutex and two condition variable, empty CV and full CV. So if the buffer is empty, then consumers will wait using this empty CV. And if the buffer is full, then producers will wait on this full CV. So inside the produce function, we're going to acquire the lock. We're going to wait here. So we're going to check if the size is max, then we're going to wait. So here I'm using while. So I keep checking and then putting myself to sleep. I will definitely talk about why not if. So why not just have an if instead of while? Just check once. We'll talk about it. Here, if I get out of this while, then that means that the queue now has a space. So I can add the item that I want to produce. And once I add, then I can signal potentially those consumers that are waiting for a new item. And then I unlock. And then in consume, I do this the opposite direction. I lock again. Now I wait. If the queue is empty, I wait on this empty CV with my mutex. Again, why while? We'll talk about it. If I get out of this, it means that the queue is not empty. Now I can remove one item. And when I remove an item, now there is an extra space on the queue that could be filled. I can signal any producer that is waiting on this full CV. And after I do this, I call unlock and I return. So this is just one example. Here, when we signal on empty, somebody is going to wake up here. Not immediately, but somebody is going to be scheduled to later on wake up. And when here I call full CV.signal, then I'm basically waking up someone here. And again, by waking them up, I'm just making them ready. So whenever a scheduler decides to run them, they're going to wake up inside this wait function. One last thing to say before we end this lecture is that when a thread wakes up inside its wait, it has to reacquire the mutex before getting out of the wait function. So inside the wait, before it goes to sleep, it will release this mutex so that other threads could use it. And then it goes to sleep. Then somebody signals, and by signaling, that thread that was put to sleep will be ready now. Now, at some point, the scheduler will schedule that thread. The thread starts running inside this wait function. That's where it went to sleep. Now it wakes up there. So the first thing it does, it acquires or it locks the mutex. So that's what it has to do. So when it comes out of this wait, the assumption is that I have the mutex. So that I have this invariant that inside this, the lock is acquired by this producer. Because in this function, I basically released the mutex, went to sleep. When I came back, I should acquire it before getting out of this wait. Because when I'm out of this wait, I'm actually inside this critical section. And in this critical section, the assumption is that the mutex is locked. So these are, hopefully you have been taught all of this. If not, definitely take a look at the slides. And again, in the next lecture, we will talk about why this is a while and not if, and then we'll see the implementation of condition variables. I'm going to stay in the meeting after I end this live session. So if you have any questions, use the Q&A, and I'll answer for 5-6 minutes afterwards. And then after that is my my office hours. Okay, with that, I end this lecture. Take care, be safe. We'll talk to you on Friday. Bye-bye.